The African, Arabian, and Indian plates collide with the southern margin of the Eurasian plate along a 1,200-kilometer convergent boundary. This has resulted in a mountain chain that stretches from the Alps to the Himalayas. Whereas divergent, transform, and subduction zone plate boundaries produce relatively narrow belts of earthquakes, continent-continent collision produces broad earthquake zones. Let's go back 60 million years to understand the plate tectonic history of the Himalayan region. About 50 million years ago, the Indian continent collided with southern Eurasia and began constructing the Himalayas and the Tibetan Plateau, the highest mountain range and the largest continental plateau on Earth. Regional compression produces broadly distributed earthquakes north of the 2,900-kilometer Himalayan plate boundary. However, the historical earthquake record indicates that the largest earthquakes, shown by their rupture areas, occur on the shallow portion of the megathrust boundary. The magnitude 8.6 Assam-Tibet event in 1950 was the 10th largest earthquake of the 20th century. On April 25, 2015, the magnitude 7.8 Gorkha earthquake started 15 kilometers beneath the epicenter northwest of the Nepal capital of Kathmandu and ruptured 100 kilometers toward the east. To understand the Gorkha earthquake, let's look at a north-south oriented cross-section through the Kathmandu Basin. Geological studies and seismic imaging reveal a complicated history of faulting and earthquakes in the Himalayas, but here we focus on the active main Himalayan thrust fault. The Indian plate pushes the leading edge of the Eurasian plate northward, shortening the overriding crust by over 2 centimeters per year. On the deeper, low-friction part of the plate boundary, displacement occurs by slow creep, with few earthquakes. In the 15 to 20 kilometer depth range, frequent magnitude 3 to 6 earthquakes occur on the megathrust plate boundary. The shallow part of the fault is locked by high friction, and stress increases during motion on the fault at deeper levels. During the Gorkha earthquake, that stress overcame friction, and the overriding Eurasian crustal block lurched southward. Maximum displacement of 3 meters occurred on the megathrust about 20 kilometers north of Kathmandu, but the fault did not rupture to the surface. This displacement uplifted Kathmandu over 60 centimeters and moved the city 1.2 meters south towards India. A GPS station in the Kathmandu Basin recorded the ground motion, while video captured people's response. Following ground motion of 1.5 meters to the southeast over the first 10 seconds, the ground lurched 1.6 meters west in less than 3 seconds, causing people to stagger and some to fall. Over the next 12 seconds, the ground moved back and forth 3 times, with an average time of 4 seconds for each oscillation. This motion, with 4-second period and decreasing amplitude, continued for another minute. The Kathmandu Basin is a broad valley in the foothills leading to the high Himalayas. This valley was formerly the site of a lake, within which up to 600 meters of thickness of river delta and lake sediment accumulated. Compared to bedrock around and beneath the basin, seismic waves from the Gorkha earthquake caused these lake sediments to shake like jello in a bowl as they reverberated or resonated back and forth with a period of 4 to 5 seconds. The good news is that well-constructed houses of 1 or 2 stories withstood this 4-second period ground shaking with minimal damage. The bad news is that tall structures, or poorly constructed buildings, were vulnerable to the prolonged ground shaking and preferentially collapsed, accounting for many deaths and injuries. Even more deaths and injuries occurred in the rural areas north of Kathmandu over the center of the rupture zone, primarily due to very weak building construction practices. Tens of thousands of landslides, ranging from small rock falls to fatal rock and ice debris avalanches, occurred during the ground shaking from the Gorkha earthquake and its aftershocks. The most deadly was the Langtang debris avalanche that slid as much as 1,500 meters downslope, then became airborne and plunged an additional 500 meters, burying the village below and killing 200 people. A lateral compressive air blast knocked down houses nearby. It is noteworthy that this magnitude 7.8 earthquake produced fewer landslides, less damage, and a smaller number of injuries and fatalities than seismologists expected for an earthquake of this magnitude in Nepal. In part, the lesser impact is a result of the slow rupture velocity due to the complex geology in this continental collision zone. More importantly, rupture during the 2015 Nepal megathrust earthquake did not reach the surface, so ground shaking and associated effects were less severe than what have occurred during a shallower earthquake of similar magnitude. Because large amounts of water are provided from Himalayan snow and ice melt, the area south of the mountain range has become densely populated. Since 1950, India's population has grown from 360 million to 1.3 billion people today. When we overlay the seismic hazard map, we see a confluence of high population density and countless vulnerable structures within areas susceptible to strong shaking during earthquakes. Near-boundary cities such as Delhi, with a population of 11 million, may be particularly vulnerable to a megathrust earthquake that ruptures to the surface along the thrust zone. Strong buildings and community planning are essential to hazard mitigation.